This will be a fairly short video on the effect of intermolecular forces on physical properties of the molecule, and this is in the context of organic molecules only. So we're going to talk about the physical property boiling point predominantly, but other physical properties include melting point, vapor pressure, that is the ability of a liquid to evaporate or form a gas, solubility and viscosity. All of these properties are due predominantly to the intermolecular forces that these molecules exhibit. So when we look for intermolecular forces, we first have to look at the type of the functional group and whether that group is polar or not. So a polar functional group is going to influence intermolecular or physical properties far more than a nonpolar functional group or nonpolar molecule. So if we want to talk about boiling point, we look at polarity of the functional group, and then we ascertain molecular polarity. But we also have to consider the length of the hydrocarbon chain and how that affects surface area or exposure of a functional group. I'll talk more about that in a minute, but realize that a hydrocarbon chain in itself is going to be a nonpolar entity in that molecule, and so that will influence the boiling point of a molecule, as we'll see. First of all, we have to really consider the functional groups, and so just to remind you of the different functional groups here, haloalkanes. This is the carbonyl group, and so that would be aldehydes and ketones. This is the ester functional group. This is a tertiary amine group, and I say tertiary for a reason. I'll get back to that. And then this is the ester group. So those 5 functional groups would all exhibit the type of intermolecular force known as dipole-dipole, because these are all going to be polar molecules. So these all show the dipole-dipole forces as a minimum. Okay, so let's look at quickly look at why. So if we have a haloalkane with a carbon-fluorine bond, for example, that's definitely a polar bond. Delta negative around the fluorine, delta positive at the carbon end, so the molecule itself will be polar. That would change if I had 4 fluorines attached instead of hydrogens. If I have tetrafluoromethane, it would actually end up being nonpolar because all of the dipoles, the bond dipoles, would cancel each other out. Carbonyl group, so aldehyde or ketone group, is also a polar group. The C double bond O is polar. And again, so aldehydes and ketones have a polar aspect to the molecule. Now, interestingly, the position of that carbonyl group is going to affect boiling point. Terminal carbonyl group you see in an aldehyde would be considered to be a highly exposed functional group, whereas a carbonyl group within a chain, like you'd see in a ketone, would be a less exposed group. And so the more the exposure, the greater the influence of that group. And since it's polar, that's going to affect boiling point. Ester group, also polar, delta negative towards that oxygen, delta positive towards the carbons of the R groups. And so molecular polarity kind of goes that way. And so it's a polar molecule. But again, that functional group, that C bond O group, is somewhat closed off because of the alkyl groups that are on either side of it. Tertiary amine, again, polar. So all of those carbon to nitrogen bonds would be polar bonds, and because of the shape of around that group, it's going to be a polar molecule. But again, greater the influence of the nonpolar R groups if they increase in chain length. And finally, ester has 2 kind of orientations for polarity because of the C double bond O and the C single bond O, and so again that gives rise to a polar molecule. So these particular functional groups would all give rise to dipole-dipole forces as the predominant or strongest type of intermolecular force. Now these functional groups. So here we have alcohol and carboxylic acid and amine. Now this is primary or secondary amine, and again I mentioned tertiary was one type. Primary and secondary are a different type. These functional groups all give rise to hydrogen bonding between these molecules. So remember, hydrogen bonding in the organic context is H bonded to oxygen or nitrogen. And you can see we have that in all these functional groups. In alcohols, oxygen bonded to hydrogen, delta negative around the oxygen, delta positive around the hydrogen. Hydroxyl group on the carboxylic acid. So that again is going to be very similar to what the alcohol would look like. And so in a primary secondary amine, because there's hydrogen bonded to the nitrogen, we're going to have polarity around that bond, and that intermolecular force would be hydrogen bonding. So that's going to be a stronger intermolecular force. So we would predict polarity is going to, or boiling point is going to change based on the fact that it's hydrogen bonding. So when we want to talk about the relative strengths of intermolecular forces, we typically look at keeping it fairly straightforward. We're not changing too many things, not changing too many variables. So if we look at this as an initial example, we have three different molecules here, all with different functional groups per se. So we have an alkane, so that's a non-polar molecule. Ethoxyethane, so here's my ester or ether group. So that's delta negative, so that's going to give rise to polarity in that molecule. And then we have the hydroxyl group in 1-butanol. So nonpolar molecule through to very polar in terms of the functional group. Remember, the OH group gives rise to hydrogen bonding. That's a strong intermolecular force. So we would predict that butane being nonpolar would have the lowest boiling point. BP, short for boiling point. It's pretty commonly used. And then the boiling point is going to increase from there. So ethoxyethane shows dipole-dipole forces. But butane-1-ol has stronger hydrogen bonds, hydrogen bonding. And so it will have the highest boiling point. And so if we look at the boiling point, that's confirmed. Okay, so methane, boiling point of around 0, butane, boiling point of around 0, ethoxyethane 35 degrees Celsius, and butane-1-ol much higher, 117. So it really gives you an idea how much stronger those hydrogen bonds are as forces of attraction. We can see the same thing here with these two similar molecules, similar molecular mass, so it's not going to be due to dispersion forces, which we'll get to in a minute. But if we were to predict boiling points, we'd probably consider, because the methylpropanoate has polarity there and polarity there, so that's two orientations for delta positive, delta negative, so you can form intermolecular forces there between neighboring molecules, but that's dipole-dipole. And again, butanoic acid also has dipole-dipole forces because of that C double bond O, but again, here we have hydrogen bonding. And so if we were to predict, we would predict butanoic acid would have a higher boiling point whoops, let's just get rid of that, has a higher boiling point due to the presence of hydrogen bonding. And again, they both have the carbonyl group, so that will not cause the boiling points to be different between the two. Methylpropanoate has that C single bond no polar component, but that would not provide as strong intermolecular forces as the hydroxyl group and the hydrogen bonding that comes with it. So again, butanoic acid, double the boiling point of methylpropanoate. So it's a strong intermolecular force, that hydrogen bonding. So as I mentioned, size of the molecule, that is, you can look at this as molecular mass, you can look at this as number of electrons, because this here now we're talking about dispersion forces. And so dispersion forces are due to the number of electrons, which we can equate to the size or mass of the molecule. So dispersion forces at play here, so clearly the more electrons, the more you the greater number of different polarized orientations of the molecule. That is, you can have greater electron disorientation and more intermolecular forces of attraction. And so again, for this, it's pretty straightforward. We'd predict propane boiling point. Let's get boiling point of propane to be less than butane, to be less than pentane, to be less than hexane, and all because the molecule is getting larger and therefore more opportunities for those dispersion forces. These are all chain, so we're not looking at surface area effect per se, we're just looking at size of the molecule. We can see that in the alcohols again, so if you predict this, it's kind of already in order, but they all have the same functional group. It's just a matter of the size of the molecule. As we add more CH2 groups, we increase the amount of dispersion forces. So this increase in BP boiling point is due to added strength of dispersion forces only. They all have the OH group, so they're all exhibiting hydrogen bonding. So it's not that, it's because we have larger molecules. So increased size, increased strength of dispersion force. Now we've already looked at this one in class, but I'll just go through it again. This is where we look at surface area or exposure. Now the first case is purely a case of surface area. So pentane has a long chain. Well, there's my long chain. There's no long chain, so I can establish forces all along that chain. And if they weren't nicely aligned, well, I don't get quite as many forces of attraction, but I can still establish more force of attraction. With our 2,2-dimethylpropane, basically, I'm getting almost really, looking at it, a single point of contact. So that's the only contact or only area for dispersion forces. And so I'm not establishing as many. And so we would obviously predict that that's going to affect boiling point, and it affects boiling point in predictable fashion. 2,2-dimethylpropane with fewer points of contact with a smaller surface area for contact for dispersion forces has a lower boiling point. And finally, if we look at, this is where we're talking about the exposure, and by exposure we're talking about exposure of the functional group. So if we look at pentan-1-ol, the functional group is terminal, and so that kind of frees that up to interact with other functional groups of other pentan-1-ol molecules. It's right at the end, kind of open, a bit wide open. Pentan-3-ol on the other end has that hydroxyl group within the chain, and so these alkyl groups are kind of interfering or getting in the way a little bit. And so the exposure of the functional group is a little less. And so if the exposure is less, if there's less chances of forming contacts, that is hydrogen bonds between molecules, less chance of forming the contacts, the lower the boiling point. And so if we were to predict boiling point of these, so we'd predict that butane-1-ol or pentane-1-ol has a higher boiling point. And indeed it does. It has a boiling point about 20 degrees lower. So it definitely is affected. Still a high boiling point because it's an alcohol and it's hydrogen bonding, but because of the position of that hydroxyl group, not quite as readily available for formation of stronger hydrogen bonds. And that concludes this video.